Welcome to today's paper reading. Today's paper is titled, DVLO, Deep Visual-LiDAR Odometry with Local-to-Global Feature Fusion and Bidirectional Structure Alignment. This paper was published on AR14 by Jiuming Liu and colleagues from Shanghai Jiaotong University and University of California, Berkeley. In this study, the authors introduce a local-to-global fusion network called DVLO, which features bidirectional structure alignment. To achieve local feature fusion, points are projected onto the image plane to serve as cluster centers, around which image pixels are grouped. These image pixels are pre-organized as pseudo-points for image-to-point structure alignment. Subsequently, points are converted into pseudo-images through cylindrical projection for point-to-image structure alignment. The method then performs adaptive global feature fusion between point features and locally fused features. The proposed method demonstrates state-of-the-art performance on the Kitty odometry and Flying Things 3D scene flow datasets, outperforming both single-modal and multimodal methods. The source code for this method is available on GitHub. The DVLO network introduces a novel approach to multimodal odometry by implementing a local-to-global fusion strategy with bidirectional structure alignment. This method involves treating images as sets of pseudo-points for local fusion with LiDAR points, and converting point clouds into pseudo-images through cylindrical projection for global adaptive fusion. A key innovation is the clustering-based local fusion module, which aggregates pseudo-point features dynamically based on similarities to cluster centers. This approach not only provides fine-grained point-to-pixel correspondence information but also enhances global information interaction due to its larger receptive field. The contributions of this work include the proposal of a new fusion network, the first deep clustering-based multimodal fusion, and demonstrated superior performance on the Kitty odometry dataset compared to recent methods. Figure 1 illustrates various fusion strategies employed in the context of images and points. Traditional approaches predominantly focus on either global, 53, or local, 73 fusion. In contrast, our proposed DVLO method introduces a novel local-to-global fusion strategy. This approach not only facilitates the interaction of global information but also preserves the fine-grained details inherent in local features. Additionally, a bidirectional structure alignment mechanism is incorporated to enhance the complementarity between the two modalities. This dual alignment strategy ensures that the fusion process is both comprehensive and efficient, addressing the intrinsic structural inconsistencies between image pixels and LiDAR points. In the field of dynamics removal, NOR-FEO stands out by optimizing a set of keyframe poses and enhancing the geometric accuracy of the scene representation through volume rendering. Moving to deep LiDAR odometry, the task remains challenging due to the irregular and sparse nature of LiDAR points. Nikolai et al. Were among the first to introduce deep learning techniques into this area, focusing on pose estimation through 2D depth images. Lastly, Visual-LiDAR Odometry has gained attention for its ability to leverage both 2D and 3D features. This area is divided into traditional methods, which refine motion estimation using visual odometry as a prior, and learning-based methods, which fuse RGB and depth images. Our work introduces the first Visual-LiDAR Odometry network with bidirectional structure alignment, addressing the inconsistency between natural data structures of points and images. The proposed DVLO architecture begins with the input of 2 point clouds, PCS and PCT, and their corresponding monocular camera images, IS and IT. The primary objective is to estimate the relative pose between these two frames, which includes both the rotation quaternion Q and the translation vector T. The process starts with hierarchical feature extraction, where the point clouds are projected onto a cylindrical surface to facilitate orderly organization and feature extraction. This step yields multi-level image features and point features. Following this, the local-to-global fusion module is employed. This module includes a local fuser that merges fine-grained features within clusters, and a global fuser that enables global information interaction between modalities. Finally, the pose is iteratively refined from the fused features, enhancing the accuracy of the estimated pose. Figure 2 illustrates the pipeline of our proposed DVLO, which includes a novel local-to-global, LOGO, fusion module. This module is composed of a clustering-based local fusor and an adaptive global fusor. The pose estimation process begins with the cost volume of the coarsest fused features and is iteratively refined using fused features from shallower layers. The local fusor enhances fine-grained feature fusion within clusters, while the global fusor ensures broader information interaction across the feature maps. Figure 3 illustrates the local-to-global (LOGO) fusion module. The process begins with projecting points onto the image plane using a coordinate system transformation matrix, which serves as the basis for cluster centers. Subsequently, the image is converted into a set of pseudo-points. The module then proceeds to locally aggregate pseudo-point features by evaluating their similarities to each cluster center. This approach facilitates efficient and effective feature fusion, enhancing the overall performance of the system. Table 1 presents a comprehensive comparison of various odometry networks on the KITTI odometry dataset. The metrics used for evaluation are the average sequence translational RMSE, TREL, and the average sequence rotational RMSE, REL, both measured in specific units over subsequences of varying lengths from 00 to 10. The table highlights the best and second best performing models, with an asterisk indicating those trained on sequences 00-08. This comparison is crucial for understanding the relative performance of different odometry methods in real-world scenarios, providing insights into their accuracy and reliability. In this experiment, the KITTI sequences numbered 00 to 10 are utilized for both training and testing purposes. The focus is on comparing the performance of traditional Visual-LiDAR odometry methods with the proposed approach on these sequences. The experimental setup involves using these sequences to train the model and subsequently test its effectiveness. This comparison is crucial for evaluating the advancements made in Visual-LiDAR odometry techniques. Table 2 presents a comparative analysis of Visual-LiDAR odometry methods on the KITTI 00-10 sequences. Our DVLO, trained on sequences 00-06, demonstrates superior performance in terms of translational RMSE, TREL, across multiple sequences. Notably, DVLO achieves the best TREL in sequences 04, 06, and 07, outperforming traditional methods like VLOM, DVL-SLAM, and PL-LOM. The mean TREL for DVLO across all sequences 00-10 is 0.67, which is notably lower than the mean TREL of 1.38 for VLOM, 0.98 for DVL-SLAM, and 0.94 for PL-LOM. This indicates that DVLO provides more accurate odometry results, highlighting its effectiveness in integrating visual and LiDAR data for precise localization. The DVLO model was trained on sequences 00 to 06. The best performance results for each sequence are highlighted in bold, while the second best results are underlined. When compared to other methods such as VLOM, DVL-SLAM, and PL-LOM, our method demonstrates superior performance across most sequences. Specifically, the mean translational error, TREL, for sequences 00 to 10 is 0.67, indicating a significant improvement. Additionally, our DVLO outperforms visual odometry, VO, and LiDAR odometry, LO, networks, with a 63.4% decline in translational error, TREL, and a 43.8% decline in rotational error, REL, on sequences 07 to 10. Figure 4 presents the trajectory of our estimated pose, illustrating both 2D and 3D trajectories of our network alongside the ground truth trajectory on the KITTI dataset. This visualization aids in understanding the accuracy and reliability of our pose estimation method by comparing it directly with the ground truth data. The inclusion of both 2D and 3D representations provides a comprehensive view of the trajectory, highlighting the effectiveness of our approach in tracking the actual path taken. Figure 5 presents the trajectory results of our method and LOM on the KITTI sequence 07, including the ground truth for comparison. The figure clearly shows that our method outperforms LOM in both scenarios, without and with mapping. This demonstrates the superior performance of our approach in localization tasks, even when not integrated with a mapping component. Figure 6 illustrates the local clustering-based fusion mechanism designed in our method. The red points represent the 2D positions of cluster centers, while the yellow regions depict the clustered pixels around each center. This clustering is achieved through pointwise cosine similarity calculations, ensuring that pixels with similar texture information are accurately grouped together. Figure 7 provides a visualization of the estimated scene flow from our method. The blue points represent the source points in the scene. The green points indicate the correctly estimated target points, while the red points highlight the incorrectly estimated target points. This visualization helps to illustrate the accuracy and effectiveness of our scene flow estimation technique. Table 3 presents a comparison of learning-based multimodal odometry methods on KITTI 09-10 sequences. Our DVLO method, trained on sequences 00-06, is contrasted with other models trained on sequences 00-08. The table highlights the best and second best results through bold and underlined text, respectively. This comparison underscores the performance of DVLO in relation to other state-of-the-art methods, demonstrating its effectiveness even with a smaller training dataset. Table 4 presents the average inference times for various multimodal odometry methods applied to the sequence 07-10 of the KITTI odometry dataset. The methods compared include DVLO, PLO, Zhuo, et al., and our method. DVLO has an inference time of 167 milliseconds, PLO takes 200 milliseconds, and Zhuo requires 143 milliseconds. Zhuo et al. Achieve an inference time of 100 milliseconds, while our method records the fastest inference time at 98.5 milliseconds. This comparison highlights the efficiency of our method in processing multimodal odometry tasks. Table 5 presents a comparison of various scene flow estimation methods on the val split of the Flying Things 3D subset. The table categorizes methods by their input types, which include RGB images, XYZ point clouds, and combinations of both. Key metrics such as 2D endpoint error, EP2D, 2D accuracy within 1 pixel, ACC1px, and 3D endpoint error, EP3D, are used to evaluate performance. Our method, which utilizes both RGB and XYZ inputs, achieves the best results in EP2D, 1.69, ACC1px, 87.6%, and EP3D, 0.048, demonstrating superior accuracy and efficiency in scene flow estimation. Table 6 evaluates the significance of the local fusor, LOF, and global fusor, GOF, in the local-to-global fusion network. It presents the best results for each sequence in bold. The table includes metrics such as TREL and REL for sequences 07-10, showing the mean values for these metrics across the sequences. This analysis helps in understanding the contribution of each fusor module to the overall performance of the network. Table 7 presents the results of ablation studies comparing different local fusion strategies. The clustering-based local fusion strategy demonstrates superior accuracy, achieving the highest results among the methods tested. Notably, this strategy also significantly reduces inference time, requiring only half the time of attention-based methods. Additionally, it outperforms the convolution-based strategy in terms of accuracy. These findings highlight the efficiency and effectiveness of the clustering-based approach in multimodal feature fusion tasks. Thank you for watching.